Okay, so here's what we've got. Okay, we're going to look at balancing chemical equations. Okay, let's look at, we'll look at kind of one of each so we can also review the reaction types. Okay, so let's start out with, and we'll also look at predicting, because that way we can cover kind of everything to do with reactions that way as well. Right? Oops, no, that's not right. CA. Okay, so we've got one of each reaction type here. So if we're going to predict the products of a chemical reaction, the first thing that we have to remember is what kind of reaction is going on. Right? In our first reaction, I have two elements reacting with one another. Who remembers what kind of reaction that is? That's a synthesis reaction. In a synthesis reaction, I make a single compound out of the two elements. Okay, I've got nitrogen and I've got lithium. What order should that compound go in? Lithium first, nitrogen second, because it's going to make an ionic compound and metals always go first. All right, so I've got those now together in the right order, but it's an ionic compound. So I need to write down the charges, -3, +1, and then drop and swap. So I'll have Li3N as my proper swap and dropped ionic compound. Now I've got a balance. Okay, so I pick the thing present in the highest number. Right? The thing present in the highest number right now is lithium. But if I just go over here and put a 3 there, that's not going to balance my nitrogens, is it? Because I'm going to have to come back and put a 2 here to balance nitrogen anyway. So I'm going to do that, okay, which is going to give me how many lithiums? 6. All right, so I'm going to put a 6 there, and now I've got 2 nitrogens on each side, 6 lithiums on each side. I think I'm pretty much done. Okay. All right, our second reaction has only one reactant, which means it's what kind of a reaction? It's a decomposition reaction. So this thing is going to break down into its two elements. Those are nitrogen and hydrogen. What do I need to remember about those two elements? They're both special and they both come as 2s. Okay, now I need to balance the reaction. Thing present in the highest number is hydrogen. There's 3 on this side, 2 on that side. What's the lowest common multiple? 6. So a 2 here balances my nitrogens nicely, and a 3 here will take care of the hydrogens. What kind of reaction is going on in number 3? Combustion reaction. Anytime we see carbon and hydrogen and oxygen together, that's what we've got. So what are always the products of a combustion reaction? Water and carbon dioxide. Okay, there's some special balancing rules to do with combustion reactions. One of the rules is that I balance them alphabetically. The second rule is the rule of 2. When do I apply the rule of 2? If there's an even number of carbons. Does the rule of 2 apply here? Yes, it does. All right, so I'm going to put a 2 there, which gives me 8 carbons. Balancing in alphabetical order. Carbons are balanced. I have 20 hydrogens. 2 times 10 is 20. So I've got to go over here and make sure I have 20 hydrogens by putting a 10 in front of the water. Now I have to balance the oxygens. I have 8 times 2 is 16 oxygens here in the carbon dioxide, and I have another 10 oxygens here with the water for a total of 26 oxygens. 13 times 2 is 26. Right? kind of reaction is number 4 with an ionic compound and an element? Single replacement. Okay, in a single replacement, to figure out who goes with who, I've got to look at what's by itself. Phosphorus is by itself, and phosphorus is a non-metal. Who's it going to swap out for? It's going to swap out the chlorine and end up with calcium. So we'll have calcium with phosphorus, and chlorine will be by itself. Single replacement reactions are the ones with the most things to look for. I have produced an element by itself, and it could be special. Is chlorine special? Yes, it is. Comes as a 2. All right. Then I have an ionic compound, which I need to drop and swap. Phosphorus is a -3. Calcium is a +2. So I'm going to have Ca3P2 when I drop and swap. All right. Now I need to balance the entire reaction. So I've got 4 phosphorus on this side. I've got 2 over here. What's the lowest common multiple of 4 and 2? Okay, well, 4, yes, is the lowest common multiple. So if I put a 2 here, that gives me 4 phosphorus on that side. How many calcium does it give me? 6. All right, so I go over here, and I put a 6 there. All right, 6 times 2 is 12, so I've got 12 chlorines. 6 times 2 is 12 chlorines, and that should take care of everything. Okay. And then our last one. Okay, I have 2 ionic compounds reacting with each other. That's a double replacement reaction. In a double replacement reaction, we swap the metals, so everything gets a new partner. So copper will end up with oxygen. Lithium will end up with nitrate. And I don't know whether that's going to need brackets, so I shouldn't put them there just yet. Okay. Now I need to drop and swap my 2 ionic compounds. Lithium's a +1, nitrate's a -1. Do I need brackets? No. Okay. Copper, in this case, what charge was on copper? Because copper has more than one possible charge. This case it was a 2 because nitrate's a -1 and there's 2 of them here. Okay, so that means copper was a 2+, oxygen's a 2-, so those work out just fine as 1 and 1. Everything's 1 and 1, okay, on that side. Now I need to balance the reaction. I've got 2 nitrates over here, and I've only got 1 over here. So I'm going to put a 2 there. That gives me 2 lithiums, and there are 2 lithiums over here, so that's looking good. 1 oxygen, 1 copper, 1 copper. Looks like we're done. Okay, is that ringing a bell for everybody? All right, so now we've covered balancing reactions, predicting reactions, and reaction types. No, that's on nitrate. Nitrate is NO3. It's a polyatomic ion, right? It's not going to break up. Okay, what else? All 4 ways, mole equation? Okay, because we talked about one of them yesterday. Okay, so let's start with the simplest one. Okay, how many moles of lithium nitrate are in 25 grams? Okay, it'd be about as simple as we could get. So, first thing I can calculate is molar mass, because they told me the compound, but I've got to write the compound correctly, or I won't get the proper molar mass. So, lithium with nitrate, right? We had this in our last question. This is a -1, this is a +1, so we're good there. Okay, now we just have to plug in our numbers. So, lithium is 6.94. Okay, plus 1 nitrogen, 14.01, plus 3 oxygens. All right, 68.95 is our molar mass. Grams per mole. Okay, everybody okay with what I did there? All right, so now I have big M, and they gave me little m when they said the mass was 25 grams. Do I have more than 1 mole or less than 1 mole here? Less. I have 25 grams, and 1 mole is 68.95. So I'm going to get a decimal here. That's okay. N equals little m over big M. 25 grams divided by 68.95 grams per mole. All right, so I have 0.36 moles. Okay, so that's kind of the easiest one. All right, so second kind, we're looking for the mass and we're told the number of moles, right? So we know that N is 14.5 moles. We're told the material is iron 3 sulfide. So iron with the 3 plus charge, that's what the Roman numeral tells us, remember, okay? And sulfide, which is a -2 charge. So we're going to have Fe2S3 as the formula for the compound that we are dealing with in this question. All right, so iron is going to be 55.85, and there's 2 of them. Okay, plus 32.06, 32.07. Is it 06 or 07 on your periodic table? Yeah, we'll say it's 7. Okay, and there's 3 of those. All right, so that's going to give us our molar mass here, so 55.85 times 2 plus 32.07 times 3. All right, so our molar mass is 207.91 grams per mole. Okay, so now I'm looking for the mass. Okay, N equals little m over big M. So to get little m by itself, I multiply both sides by big M. Big M comes over here. Now I just have to plug in my numbers. Okay, so we will have our 207.91 multiplied by N, which is 14.5. All right, so we're looking at 3,014.70 grams. Okay, I'm not worried about significant figures on your mole equation calculations, by the way. Okay. Okay, everybody good with that one? Okay, so this is the first type of question that involves the use of Avogadro's number. Yep. Okay, so what's the mass of 7.5 times 10 to the 24 molecules of magnesium bromide? Okay, so if I want to find little m, I need N and I need big M. So I can calculate big M right away. Okay, it's going to be magnesium bromide, so Mg, which is 2 plus, Br, which is -1. So we're going to have Mg, Br2. All right, so magnesium is 24.31. And there's only one of it, plus 2 bromines, that's 79.9 times 2. All right, so 184.11 grams per mole. Okay, I need to get N. Now, I know the number of molecules, and I know the number of molecules in 1 mole, because that's what Avogadro's number tells us. So if I take the number of molecules I have, 7.5 times 10 to the 24, and divide that by the number of molecules in 1 mole, that should tell me how many moles I have, in the same way that dividing 48 donuts by 12 tells me how many dozen I have. Everybody follow there? Okay. So to calculate N, okay, I'm going to go in brackets 7.5 E24 okay, divided by Avogadro's number 6.02. Whoop, not well. Okay, so I've got 12.46 moles. All right, now I have N and big M. I should be able to calculate M. So M equals N times big M when you manipulate it. Okay, so that's going to be 12.46 times 184.11. All right, so we're looking at 2,293.73 grams. Okay. Anybody still need that one? Yeah. All right. How many molecules of potassium carbonate are in 253 grams? Okay, so they're telling us the mass, 253 grams. Okay, they're telling us it's potassium carbonate, which is potassium is a +1, carbonate is a polyatomic ion, it's CO3, and it's a -2. So that means that my proper formula is K2CO3. All right, so potassium is 39.10, and there's 2 of those, plus 1 carbon, 12.01, plus 3 oxygens. Times 2 plus 12.01 plus 48. Okay, 138.21 grams per mole. Right, is our molar mass. What can I find if I have little m and big M? N. Yeah. Right, so that's probably my next step since I have those two things. 253 divided by 138.21. All right, so I'm looking at 1.83 moles. Okay, question asked me how many molecules I have. I now know how many moles I have. What am I going to do to get the number of molecules? Okay. Not divide, because then I would get a ridiculously small number. I'm going to multiply. Okay, Avogadro's number tells me how many molecules are in 1 mole. If I want to find out how many molecules I have, I need to multiply by the number of moles. Okay, in the same way that if I ask you how many donuts there are in 4 dozen, you go 4 times 12. Okay, everybody follow there. Okay, so we'll take our 183. So number of molecules equals 1.83, the number of moles, times Avogadro's number. And that'll give us our number of molecules. All right, so we're looking at 1.1 times 10 to the 24 molecules. Okay, that's all 4 ways I can ask about the mole equation. Okay, anybody still need this? All right, so if I have a position versus time graph, say it looks like this. This is in meters, this is in seconds. Okay, a position versus time graph. Okay, let's say that it has this equation: y equals 5.1x plus 3.5. Okay, so what does the 5.1 represent? It's speed. It's also the slope. Okay, the slope of this graph is speed, because if I manipulate for this 5.1, okay, so if I have y equals mx plus b, and I manipulate for m is going to be y minus b over x, which is really the final position minus the initial position, because that's what b would be, where I started from. Okay, y would be any other value where I finish. Okay, divided by x, which is time. Well, final position minus initial position over time is really just displacement over time. Okay, everybody follow me there? All right, so if you have a position versus time graph and it's asking you to calculate the average velocity, as long as it's just a line, you can use that. If it's a line with, if it's a graph that has many parts, then you'll have to go final position minus initial position divided by the total time, right, as a kind of a multi-step question. Okay, so it could, all that really could be asked of you on a graph like this would be, what's the total displacement, which is final position minus initial position, average velocity, which we've kind of shown here. Okay, if it's a line, you just do this. If it's multiple directions and multiple lines, then you still do final position minus initial position over time. It just won't be the slope of the line anymore. It'll be the average for the whole trip. Okay, another thing that could be asked would be, I say to you, how far would the object have gone if it was allowed to travel for 100 seconds? Okay, so if I give you that, how far is the object going to travel if it goes for 100 seconds? What have I given you, a y or an x value? I've given you an x, so you would be solving for y. Okay? You'd be solving for how far it's going to go, something in meters. Okay? The other way I could ask that could be, how long would it take to go 100 meters? In which case, now I've given you a y value. You're solving for how long. That's a time. You're solving for x. So you manipulate for x. That's about all you'd get for a position versus time graph. Okay? For a velocity versus time graph, let's say it just looks like this. What's this object doing if this is a velocity versus time graph? It's decelerating, right? Slowing down. Okay. All right. So let's say that the equation for this graph looks like this. Okay. Y equals negative 4.5x plus 16. All right. So that tells us that this value up here is 16 meters per second. Okay. That's what it's telling us. So on a velocity versus time graph, one of the things I might ask is, what's the acceleration of the object? All right, how do I get that? It's the slope, right? Okay, because really, if I manipulate this one for m, I'm going y minus b over x. Okay, y is in meters per second. It would be my final velocity. B is in meters per second. It would be my initial velocity. And x is time. That's our formula for acceleration. Okay, so the slope represents the acceleration on this graph. All right, other things I could ask, similar to the position versus time graph, I give you a time and ask, how fast will the object be going, or what will the velocity of the object be at time 200 seconds? Okay, so I give you an x value, you solve for y. Okay, or how long does it take the object to reach a velocity of negative 400 meters per second? I gave you a y, you solve for x. Okay, so basically that's the same, it's just different. It's it's the same, but it's different. That doesn't make any sense. It's the same calculation, but instead of solving for position, I'm now solving for velocity. Y has changed what it represents. Okay, the last thing I might ask you would be, what's the displacement of the object to, let's say, time 15 seconds. So let's say that time 15 seconds just happens to be at the end of this line. Okay? How do I find the displacement of something from this kind of graph? I calculate the area underneath the line. So what I have here, though, are two shapes. I've got a rectangle and a triangle, right? I have a problem, though, in that I don't know the height of the rectangle. I also don't know the height of the triangle because it doesn't go all the way down to the bottom. So how can I find this value here? Which axis is it on? It's on the y-axis. Was I just given an x value? Right. Okay, so if I use y equals mx plus b, can I solve for what y is at time 15 seconds? All right. So y equals negative 4.5 times 15, my x value, plus 16. All right, so when we do that, okay, so we'll have, I'm hoping this works out. It might end up that that's a negative number just because I picked numbers out of my head, but oh yeah, it's definitely going to be a negative number. We're going to change that. Instead of 15, we're going to make it 1.5, and then it'll work out better. It'll actually be above the x-axis. If I make it 15 seconds, the line will be down there on the floor, right? And that's just going to make our life difficult. So, okay, for simplification's sake, we're going to say negative 4.5 times 1.5, okay, plus 16. Okay, so the y value there is 9.25 meters per second. Okay, can I now calculate the area of this rectangle and the area of this triangle? Yes. Okay, so I go 9.25 times 1.5, and it gives me this area. I go 16 minus 9.25 to get the height of my triangle. Multiply that by 1.5, divide it by 2 because it's a triangle, add them both together. I've got my total displacement. Okay, those would be the kinds of things you'd be asked to do on your final exam with those two graphs. Okay. No, there could be some in the multiple choice and some in the written. So there's a possibility there's more than two. Yes, yeah, there could be. So there could be a graph like this where it goes something like that. And then I might ask just what's going on in part A, what's going on in part B, what's going on in part C, part D, right? It'd be something like that. And then it's just a, okay, well, this object, sorry, this is a position versus time graph. This is an object traveling forwards at a constant velocity. This is an object traveling backwards at a constant velocity. This is an object at rest. This is an object traveling forwards at a constant velocity. Well, not on this graph because it's position versus time graph. No, on a velocity versus time graph, if it was with this many different shapes, that would take you way too long. If I was going to ask you to do that, it would be a much simpler shape, kind of like what I just showed you a minute ago, right? So it wouldn't take as long. You can still demonstrate to me you know how to do it, but it doesn't take you 15 minutes to demonstrate it. Yeah. Okay, anything else? Okay, well, I'm sure some other stuff will come up. You have a review package you can start looking at. I'm sure that while you're working on that, other questions will arise. Okay, so I'll give you some time to start going through that and doing your review, and then when questions come up, just ask.